our final video in uh, this section is called, it's about what we call inductive reasoning. And you didn't know it, but that's what we've been doing throughout this section. Inductive reasoning, and I will write this out. Let's share and make kind of a definition of what we've been doing. Uh, so inductive reasoning is basically making some sort of observation, right? And then uh, we are making informed guesses based on patterns. Making informed guesses based on patterns. That's what inductive reasoning is, right? We observe something and we notice a pattern, and then we draw some sort of conclusion, which is an informed guess. So my question for you to consider then is, well, what's good about that and what's bad about that? Maybe even pause and think about it. So really, as humans, observing patterns is one of the things our brains are sort of wired to do. Evolution has made us really good at that. It's helped us survive over time. Um, we're designed. They're designed to make these observations and draw conclusions. It helps us be more efficient with how we think and how we make decisions. But it can also be a problem because it can sometimes lead to uh, biased thinking, right? Or illogical thinking if we're not careful. We have to be careful with how we're thinking about things. We can draw incorrect conclusions because we just noticed a pattern which may not always be true, right? So you always have to make sure to validate your conclusions with additional information, with additional evidence, with additional methods. Think about how our news, the political realm, when we're inundated sometimes with information and data, numerical data, often those data are manipulated to convey a certain message, right? And it's essential that we understand how those data are collected, how they're gathered, how they're analyzed, um, because misleading conclusions can arise if biases are involved in the data, if inadequate sample sizes are involved in the data. And so we can't, it's always important that you are a bit, I don't know, bit skeptical of data, right? Make sure that you verify sources, that you verify that um, things are true. So let's explore this idea of inductive reasoning. Basically, everything you've done so far in this section has been inductive reasoning. I've given you some sort of pattern. You've continued it, but we're going to do one a little bit differently so far for this next one. So what I'm going to do is I'm going to make several sums of three consecutive numbers. So I'm going to give you three consecutive numbers, 2, 3, and 4. And what I'm going to do is add them. 2 plus 3 plus 4 is equal to 9. And then I'm going to do it again. 4, 5, and 6. Three consecutive, not just numbers, but integers, natural numbers. 4 plus 5 plus 6 is what? 15? Yeah. Let's do another one. 7, 8, and 9. 7 plus 8 plus 9 is equal to 24. So I did three of these where I added three consecutive numbers. And do you notice anything about the solutions to these, about the sums? Is there anything that you notice about them? One of the things I notice about them is that these are all divisible by the number 3. 9 divided by 3 is 3. 15 divided by 3 is 5. 24 divided by 3 is 8. They're all divisible by 3. So my question is, can we draw a conclusion that any 3 consecutive whole numbers, we'll say, actually, I said the sum of, let's rephrase that, the sum of any 3 consecutive whole numbers is divisible by 3. So how do we do this, right? We've just sort of like used inductive reasoning. We've observed a pattern and we've kind of made an informed guess. So therefore, we might assume the pattern holds true. So maybe we start by testing a couple more. Let's just do 10, 11, 12. 10 plus 11 plus 12 is equal to 33. Is 33 divisible by 3? Yeah, it's 11. So that one checks out, right? We're finding things that check out. Maybe do one more. Let's do something simple. How about 1, 2, 3? 1, 2, 3. 1 plus 2 plus 3 is equal to 6. Is that divisible by 3? Yep, we got a nice whole number. So that's 2. So proving something's true is a lot more than just what we're doing. You just can't look at examples. And there are other entire mathematical courses that teach you how to prove things. Basically, we can't right now prove that this is true, that the sum of any 3 consecutive whole numbers is divisible by 3. Inductive reasoning doesn't prove things. It's based on just observations. There could be exceptions. We just haven't found any yet. So I'm going to do a different problem. There is, by the way, there is a way to prove that any 3 consecutive numbers is divisible by 3. We're just not going to see it here. Again, that's a whole different subject. We're going to do another example, something we call circle dots. And so I'm going to give you a problem, which is, you're going to want to follow along and do this with me. We are going to draw a circle. And then what we're going to, that's a bad circle, but it's okay. And what we're going to do is we're going to put a dot on the edge of the circle. Okay, we're going to start with 1 dot. And then we're going to ask how many regions are inside the circle. And what do I mean by a region? I mean the whole big sort of section on the inside, right? And so if I put, I don't know why that erased, right? If I put 1 dot, right, 1 point, how many regions do we have? 1 region. Okay, let's do it again. I make another bad circle. That's an awful circle. And I put a dot here and a dot there. And then we connect them. I don't think I said that before. We're connecting the dots. We have 2 points here. How many regions do we have? Let's use some highlighter. So I've got 1 region there, and I've changed the color of my highlighter here. There we go. I've got another region here. So what we have now is 2 points make 2 regions. What happens if we make a third circle? That's a better circle. So 1, 2, 3. So if we connect the points, all the points, there's 1, there's another, there's another. How many regions do we have? It's going to be a little hard to start doing these highlighting. So I think what I'll do is I'll just number them. Here's 1, here's 2, here's 3, and here's 4. Okay. So if I make 3 points on my circle, I ended up with 4 regions. Okay. So do you start to notice any observable pattern between the number of points and then maybe some sequence in the number of regions? 1 point, 2 point, 3 points, 1 region, 2 regions, 4 regions. Maybe make a prediction on the number of points or the number of regions in the next one. So 1, 2, 3, 4. What I would suggest you do is pause the video and continue this one, right? Do with 4 points. Do this yourself. I'll keep going. So if I make 4 points, I have to draw those 4 lines, but I also have to connect these two, right? We're connecting all of the points together like that, okay? And so if I do that, now they start to get a little small. It's a little harder to start to find all these. But I made 4 points. So I've got 1, 2, 3, 4, 5, 6, 7, 8. Okay. So 4 points gives me 8 regions. Okay. Did that hold true to what your prediction was? What are we noticing here about the number of regions as we add a new point? With 1 point, we had run 1 region, 2 points, 2 regions, 3 points, 4 regions, 4 points, 8 regions. Do we notice the pattern? The number of regions is doubling, right? Times 2, times 2, times 2. So how many do we think might be in the 5th region? Or if we have 5 points, would we expect there to be 16 regions? Well, I'm going to copy and paste a nicely drawn version of this. And maybe you try it on your own too, before I even paste it, see what it would look like. Here we go. So do we have 16 regions when we do 5 points? I'll go through and sort of identify them, right? We've got, I'm just going to do a little shading. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and 16. Hey, we did it. So do we assume this is going to hold true forever? Once we add a 6th dot, it gets pretty messy, right? It gets pretty messy. But how many regions would we expect there to be? 32? Well, let me paste the drawing of this because I've already got it done. Take a look at that. 6 points. 1, 2, 3, 4, 5, 6. How many regions? No matter how you draw this, sometimes you've got these small sections. No matter how you draw this, you're only going to end up with 31 sections, 31 regions. So this pattern that exhibited itself through the first 5 numbers, 1, 2, 4, 8, 16, all of a sudden stops once we get to the 6th point. 6 points, only 31 regions. So is it true then? Is it true then that you can determine any number in this sequence? No, we can't. It's not always going to double. What we just found is called a counter example. And if you use inductive reasoning to draw some sort of conclusion, an informed guess about something, it only takes one counterexample to undo it. One counterexample basically proves it false, right? It proves that your conjecture is false, okay? So counterexamples are kind of what you're looking for a lot of the time. Is there some way to show that what I'm thinking is not true? So to evaluate conjectures, remember a conjecture, we talked about this last time, a conjecture is a statement thought to be true but not proven. A statement thought to be true but is not proven. A single counterexample disproves that conjecture. A single counterexample disproves that conjecture. So let's try one. Let's try maybe a simpler one than the previous one. So I'm going to make a conjecture. So here is my conjecture. The sum of any 4 whole numbers is divisible by 2. The sum of any 4 whole numbers is divisible by 2. So you might start this by just picking some numbers. So let's pick 0 plus 1 plus 2 plus 3. Sum of any 4 whole numbers is divisible by 2. So if we add those up, what do we get? 6. Is 6 divisible by 2? Well, 6 divided by 2 is 3. As long as you get a whole number answer, then yes, it is. So that checked out. Okay, does that mean our conjecture is true? No, we only just found one example that worked. Let's try another one. I didn't say they had to be consecutive, did I? No. Let's try 2 plus 4 plus 6 plus 8. 2, 4, 6, 8. Well, that's going to add up to 20. Is that divisible by 2? Yeah, I got a nice whole number 10, so that checks out. What we're really doing is we're not trying to find things that support our conjecture. We're trying to find something that disproves it. So let's pick some other numbers. How about 3 plus 4 plus 12 plus 16? Any 4 numbers. Well, those add up to 35. 35 divided by 2 is 17.5, a decimal number. That is not a whole number. That 35 is not divisible by 2. So what we found here was a counter example, right? This is a counter example, which means that our conjecture is not true, right? So inductive reasoning, it helps us identify patterns, but it does not guarantee absolute truth. You have to test things with examples, search for counterexamples, and in higher mathematics, right, you're going to use this type of reasoning as foundational for exploring all sorts of theorems and conjectures. So we're going to finish this video out going back to problem-solving strategies. And we talked about several in the previous section, but we're going to look at one more here. This is one of my personal favorites. I use this all the time. Solving a simpler problem. Right? We've got some sort of unknown situation that we have to solve the problem. And sometimes the numbers or the situations can be complex. They can be inconvenient numbers or really challenging numbers. And so sometimes using smaller numbers or just numbers that are easier to work with, try one of those first, like make up your own problem that's similar, but just with easier numbers. That can help you figure out how to solve the problem. An example that I often do when I'm teaching a class on sort of basic mathematics is when we have to work with fractions. A common question is something like this. Here are 2 fractions, 15/16 and 16/17. And I say, which of these numbers, which is bigger? Which of these numbers is bigger? Which fraction has a bigger value? And not everybody knows. Maybe you don't know, and that's okay. But one of the things that you can do when you're testing fractions is you can draw a picture of a fraction, right? So I might take a circle and cut it up into 16 pieces. This is going to be a little tricky with this digital device. There's 8. I got to cut these all up in half one more time. Oh, it's getting rough. Right. So the more we have, the harder it gets to do. But there's 16. And 15 16ths, we'd have to shade 15 of these, right? So if I shade 1, 2, really all of them, but just one, right? I'm shading all of these. This is what 15 16ths would look like, all right? That much of the circle. We would leave one section unshaded. Well, if I have to do that with 17, 17 is a lot harder to draw, cutting up into 17 equal sections. So, boy, is there another way we could do this besides? And one way you can do it is make an observation. The fractions that I gave you, did you notice that the numerator is one less than the denominator? 15 is one less than 16, and that's the same thing here. The numerator is one less than the denominator. So one thing that I always like to do is I say, try this with smaller numbered fractions, right? Try it with something like comparing 2/3 and 3/4. A much simpler problem. Which of these fractions is bigger? Well, it's easy to draw a picture of what 2/3 looks like. I cut my circle into 3 sections, and I shade 2 of them. If I draw 3/4, I cut it into 4 sections, and I shade 3 of them. So the question then, which of these is bigger, should become apparent to you. Bigger means it's got more stuff shaded. Well, look at the size of the unshaded sections. This is smaller than this one. So I would say, just based on the picture, 3/4 is the bigger fraction, right? 3/4 is a bigger number because it has more of its section shaded. Okay, so can we use that information to help us with the previous problem? I think so. The fraction with the bigger denominator, right? As long as our numerator is just one smaller than the denominator, then the fraction with the bigger denominator is going to have the bigger value. All right, it's got that same sort of pattern. So if we shaded in 16/17 of this circle, we can state that we would see 16/17 is the bigger fraction by using a similar problem with smaller numbers. Here's another one. This is what's called the handshake problem. This is again, one of my favorite mathematical problems. This will be our last one. And so my question to you is, in this is kind of hard to write out. Let me do, I'm going to type it. I'm going to type it. So let's do, okay. In a group of 15 people, how many handshakes occur if everyone must shake everyone else's hand? So if there are 15 people in a group, how many handshakes occur if everybody must shake everybody else's hand? So I'm going to let you just pause and think about that for a second and see if you can come up with a way that you might solve this problem. I'll start the process. So what we might do is start with smaller numbers first. Let's look at some smaller groups, right? Let's start with easier numbers. And pictures are going to help us in this process. So let's just say there's one person in a room. There's the one person. I'm representing that person with a dot. So how many handshakes occur when there is just one person? How about 0? 0 handshakes occur. Okay. What if we have 2 people in a room? There's a person and there's a person. And so I'm just going to draw a line between them to say there's the handshake. 1. So the number of handshakes is 1. All right. What if we have 3 people in a group? 1, 2, 3. So where are the handshakes? Here, here, and then these 2 also have to shake hands. So that's 1, 2, 3. So One person, 0 handshakes. 2 people, 1 handshake. 3 people, 3 handshakes. Any observable pattern yet? Nah, not really. Let's keep going. 4. So person, 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 person. Let's count the handshakes. 1, 2, 3, 4, 5, and 6. Everybody shook 3 people's hands. 1, 2, 3, 1, 2, 3, 1, 2, 3. Yep. So 6 handshakes. Okay. How about 5? Here it starts to get a little trickier. So we'll draw 1, 2, 3, 4, 5. So we've got, let's count them. 1, 2, 3, 4, 5 handshakes. 6, 7, 8, 9, 10. What am I missing? I think that's it. We got everybody. So that's 10 handshakes. All right. So what are we observing here? What are we observing? Is there a pattern? Oh, this looks kind of familiar, doesn't it? 0, this is to go from one number to the next of the number of handshakes. This is +1. This is +2. This is +3. This is +4. So, right, to find the number, it's almost like to find 2 handshakes, right? I'm adding 1 to 0. To find 3 handshakes, I'm adding 2. To find 4 handshakes, I'm adding 3. To find 5 handshakes, I'm adding 4. Does that look like a sequence that we've already seen? Do you remember the triangular numbers? The triangular numbers were 1, 3, 6, 10, 15, 21. Remember that diagonal of Pascal's triangle? Yeah, 1, 3, 6, 10, 15, 21. So maybe we should check one more just to make sure this all works, right? 6. Can we draw 6? 6 people. How many handshakes? You have to make this a little bit bigger the further you go. Let's count them. There's 6 people. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. I'm missing one right here. 15. There we go. 15. And yeah, that's right. 10 plus 5. And so if we go back to what those triangular numbers were, we saw that t, remember t sub 1, first triangular number is equal to 1. Triangular number 2 was 3. Triangular number 3 was 6. Triangular number 4 was 10. Triangular number 5 was 15. And what we want to find, if we go back to the problem, was what about 15 people? What's triangular number 15? Wasn't there a formula for that? It was. It was n times n plus 1 over 2. However, there's a little problem. It's a little problem. We have to be careful with this. Notice how I did triangular number 1, right? Triangular number 1, triangular number 2, triangular number 3, triangular number 4. But notice the number of people in the room. 2 people is triangular number 1. 3 people is triangular number 2. 4 people is triangular number 3. 5 people is triangular number 4. So when we want to find the number of handshakes, we're not going to go by the number of people in the room, are we? No. I'm trying to erase this. We're not going to go by the number of people in the room. We're actually going to go by one less than that. we're going to go by triangular number 14. If we continue this all the way out, the 15th person would be calculated by finding triangular number 14. It's always one less than the number of people. So we would do 14 times 15 and then divide that by 2. And if you do all that calculation, it comes out to 105. 105 handshakes would be required if there are 15 people in a room and every single person has to shake everybody else's hand. So that's where we end, right? Mathematics, it helps us recognize these patterns. We talked about all sorts of different patterns and sequences, and there were some formulas associated with those. But I'll also say it's incredibly important that we don't just rely on inductive reasoning, because inductive reasoning is not always going to prove something. We have to use other methods as well, especially with these real world scenarios. We have to apply other methods of analyzing the data and those patterns to really confirm things.